um, just giving you again very brief overview of whatever things that we have covered. We have talked about supervised and unsupervised learning. Then reinforcement learning is something different than that, in which you keep on exploring your so agent is there. It need to explore the environment, reach to multiple states, taking by certain actions, and going to get different rewards. And and um, and the requirement of such an agent is to explore it in such a way so that to achieve more and more rewards. And the important thing is that we are in RL, we are interested in future discounted reward maximization instead of the immediate rewards that you can have. So future, which is uncertain, if you wanted to do the things and maximize that reward, it need to be discounted. Give more and more weightage to the immediate rewards, and distant rewards may be given certain weight, but should not be huge amount of weightage is actually given to the distant rewards. And and we have seen that such a reinforcement learning can be modeled using MDPs. And then we have seen multiple examples by which RL can be understood well. And then we started to talk about Markov decision processes, in which we are actually having these 5 tuples, a set of probability states, set of actions that you can take, then the probability, state transition probability. So from one state, if you take an action, what is the next stage in state in which you are going to get? That is actually, all these things are actually the property of given any MDP. So if you want to solve an MDP, these 5 things are given to you. We are not drafting an MDP. We are saying that any RL can actually be somehow being modeled using this MDP. So if you want to play a game, if you can model your problem within these 5 tuples, then the solution can actually be somehow extracted or computed using the RL things. Then this is a reward function, which is saying that again, if you have S and T, then given such an S and T, probability function is going to tell you that what is the next state, and reward is going to tell you that what is the immediate reward. And this is the discount factor. We understood immediate reward as well. And then what we understood, that given such an MDP, the important thing is that how we can take an action. So that is, somehow there has to be a policy which is going to say that at any state, what sort of action that one need to take. And this is not being that is the solution that you are looking for. That you have a problem, you have drafted or somehow realized that problem in terms of MDP and in the framework of RL. Now you want a solution, and your solution is saying that if I'm at a state, is there a policy that you can tell me, that can tell the agent that if you are at any state, what is the best suited action that you can have. And this is the policy that one should have to need to somehow learn. And this policy is nothing but actually being defined as pi, which is actually the a probability function, or you can say whole probability distribution at a particular state. What is the probability that you are going to take this action? And of course, it's going to be the probability of A1 for S1, then probability of A2 at S1. So at S1, you can take A1, A2, A3, A4, and whatever possible actions, and with what probability. And there has to be a goal of such an MDP, and the goal is to maximize your DCFRs. Goal of your DCFRs are nothing but goal of your MDP is nothing but to maximize your DCFRs. And you want a policy which is not just any policy, but the best possible policy, which is the optimal policy, which is maximizing your DCFR. How we can get such a thing? And suppose that so this is small grid world problem, in which multiple states are there, and from each and every state you can go left and right. So states are there, actions are there. This is the realization of a policy, that at any state you can go in all possible direction. This is saying that if you are at this stage, then you are only moving in this direction. So this is policy number 1, which is a randomized policy. This is the policy number 2, which is slightly better than this policy. And probably how good a policy, how bad a policy, one should need to now understand that what does a policy mean, what does a good policy mean? So before that, what is the best policy? That is the optimal policy, which mean to say that at any state, at any point of time, if I know this policy, then I know the truth, which essentially mean that at any state, at any point of time, I can tell you that what is the best possible action. If you take that action, then your DCFRs are bound to be maximized. So that is the thing that that is, someone is actually we are interested in and we are looking for. And in mathematically form, pi st can actually be out of all possible pi's that you can have expected. So the expected value of your DCFR need to be maximized. So for a pi, you find out that what is the expected value of your DCFRs and maximize it, and then find out that pi which is maximizing this thing, that is your actual pi or the optimal pi that you are looking for. All these things are understood, but as soon as I say that pi, then how good a pi is, how bad a pi is, then we need to somehow figure out few things, and the few attributes that are associated to a policy, they are a value function and a q value function. Value function is nothing but saying that how good a state is. So if you are at a state S, then how good this state is means that from this S, what is the maximum DCFR that I can extract? That is the value of a state. Value of a along with this, we want to say another thing, that at S state, if I take an action A, then what is the maximum DCFR that I can achieve? That is the Q value function. In plain, simple language, how good a state is going to be governed by your value function. How good a state and an action pair is going to be governed or going to be understood by your Q function. So for any pi, for any given pi, may be optimal, may not be optimal, but just it's actually a policy, which is actually a planning, which is going to tell you that any state, how you are going to choose out of all possible action, what is the action needed to be chosen. It may be good, it may be bad, depending upon your policy. But once you fix up, say, some policy for a given policy, you can come up with a V, you can come up with a Q, and your your V is telling that how good any state is, because V is attribute of a pi for each and every state, and similarly Q pi for each and every S comma A. So with respect to given this policy, what is the best or the maximum DCFRs that you can achieve if you are at state S and take an action A? So once we define this, we also have defined this, that for any pi Vs is equal to this, which is actually maximizing this stuff, the expected value of that. So I'm sorry, that's not maximizing, but that's actually the expected reward, because here you are not maximizing. Here you are saying that, you are at here, you can go at multiple places. So if you go all different places, what is the, expected DCFR that I am going to get for this guy? So V is actually going to tell you that expected value of rewards, DCFR, that are that you are going to get for a pi. Similarly for Q, maximization is actually going to happen when you have pi 1, pi 2, pi 3, pi 4, and all possible pi's. I wanted to know that what is the V for this, 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 and for all of these V's, what's the one which is going to give me the best possible V, that is my optimal V. And I'm looking for such a pi as well, that's an optimal pi as well. Optimal Q value is again out of all of my Q, out of all of my S and A pairs. For each and every S and A pair, you are going to have multiple things that are being defined as that. Suppose that S2 comma A1, this pair I'm talking about, then you are going to have for given pi and for some given state S2. What are the things you will be having? V pi S2. Then you will be having these two things, because there are two actions possible at any state S for this state S2, say A1 and A2. For both of them, you are going to have two. With respect to this pi, you are having two probabilities that for at S2, what action that you can take, and what A1, if you take A1 action, then what's the probability? If you take A2 action, then what is the probability? And you are also interested in that what is the best possible such policy is. So again, it's being defined, q pi s comma is again being defined in this way, in which you are saying that given this policy, if you are at a state s, have taken action a, then what is the expected future reward that you can get, and that is your s comma for the q function with respect to this pi for that s comma a, which is can equivalently be written like this. Most of the things are almost clear. The only thing is that we need to understand that if this is your starting state, then r0 plus gamma times r1, that's actually the discounting that's going to happen, and this is geometrically discounting the future rewards. So gamma r1, gamma square r2, gamma cube r3, and so on. Now the point is that optimal q value function and optimal value function, what does they mean? They mean simply that out of all possible pi's, I wanted to find out that value function, that pi which is maximizing all the value functions, and that value function is the value function I'm interested in. So out of all the possible pi's that I'm having, pi 1, pi 2, pi 3, pi 4, the value function I am interested in, which is going to be my v asterisk, is the value function which is saying which is actually maximized over all the pi's. Similarly, it's actually being written for the q value function, that's q asterisk, or the optimal action value or optimal q value function, which is being represented like this as the value function. But again, that's actually the expected value and the maximization over all the pi's. So whatever the pi that you can choose, you just tell me that if I'm in state s and take an action a, what is the maximum DCFR? What is the maximum DCFR that I can somehow extract out of it? And let us understand it slightly more clearly, that if you are at a state s, if you take an action a, you are going to get an immediate reward r. We want to know that after this, what is the maximum that I'm going to get. So I'm saying that here suppose that I have reached to a state s dash, and then at s dash I can take so many different action. Out of that, someone is going to give me the thing which is better than others. You can mute your mic, please. If you have any question, then you can ask, otherwise please mute your mic. Yes. So what I was saying is that at any state where you reach after state s, if you take action this, you will reward this, and you reach to this state. Now you are you are expected to know that what is the optimal behavior after this, and if you know that, I can use that optimal behavior so as to find out the solution for this guy, that at s if I take an action a. So what does it mean is that if I know that at s dash, if I take a1, by the definition, this is saying that what is the maximum reward that you can, expected reward that you can achieve from here. What is the, reward that you can achieve from here, the reward that you can achieve from here, and the reward that you can achieve from here. So now you know that from state s dash, if you take a1, then this is the maximum that I'm going to get. This is the maximum that I'm going to get if I take a2. Then I know that out of all of them, which is the one, suppose that this is going to give me the maximum thing, so I'll choose this, and this is anyways being fixed because that's my condition. So given state this, if I take action this, I will get this reward, plus I'm going to get this reward, and that is the maximum that I can achieve. And that is why you can see that the definition is recursive, that q asterisk from s comma a is recursively being defined as this. I'm anyways going to get, that's my immediate reward, plus this is the discount factor, and maximizing all other things that I can have, that we have shown. Out of all of them, suppose that this is going to give me the maximum s dash a dash, I have said that r plus gamma and this value. One more thing that is being left, that was that if you are at state s and you take an action a, it's not always being the case that at s, if you take a action, you are always going to be at at a fixed state. It's going to be sometimes S1, S2, or S3. It's actually a distribution of states in which you can be, So that is the point, that is the definition of Q stick S comma A. That is going to be the expected value of for all the S dash. S dash is also now going to be fixed. This S dash is nothing, single fixed state. Instead, it's actually multiple states. So at S, if you take A, you are going to multiple states. So all those states are actually set of states, can be defined, as a set of states of epsilon. So for all of them, to find out the expected value of R plus gamma, we just did, that's a discounting thing. And and this is the thing, maximizing all the so maximizing, given that S dash, maximizing for all the actions. So all possible actions that you can take at S dash, you are choosing the one which is going to maximize, and expected value of that is going to tell you that what is the optimal Q asterisk S comma A. We already have covered this. So that is the Bellman relationship, which actually mean to say that if you wanted to find out thing Bellman, maximal optimal solution for this, then if you know the optimal solution for this, then I can use that optimal solution to figure out that what is the optimal solution of this. And that is why it is a recursive definition. Here you can see that this is going to be using this. So the good thing is that Q asterisk and V asterisk, both of these functions are satisfying this Bellman equation because they are optimal and they are being defined recursively. And and expected value is always being computed because of the fact that we are talking about the probability distributions, and randomness is going to be there. And because of that, we are not interested to find out the exact value and its maximization, but the expected reward maximization. Now, till now, we all understand this stuff, that given a pi, we can talk about this. Now, how can, or what is the meaning of an optimal policy? Let us see that the meaning of an optimal policy is, so the policy is that it's not dependent upon any other state other than the current state. That's why it is not dependent upon history. That's why it's Markov. Assumption is being true. At any state, you can go to multiple actions, just some repetition, and P1, P2, P3 are the probabilities by which you can go. So that is why not a fixed value, or not a fixed state in which you are going. Policy governs, one important thing is that it's going to govern the dynamics of your agent, and MDP is going MDP parameters are governing your game equations. Or suppose that you have a game, you wanted to realize it into some RL equation, RL realization. Then you need to define that 5 tuples of your MDP, and your game dynamics is actually being governed using that MDP. Policy is governing the way in which your agent is going to somehow explore the environment, and policy is not being defined. We need to define it, as well as we have to refine it as well. So best optimal policy is needed to be ensuring the maximum future reward. And and the important thing is that we are not in, we do not care the historical rewards accumulated. We are interested in discounted rewards, discounted cumulative future reward, and its maximization. Now, given our MDP, how can we somehow, so this was the whole things that one should have to first understand, that what is the MDP, what are the solutions for such an MDP, which are actually pi's. But for each and every pi, you can understand what is Q and what is V. These are the things which are related. And then we talk about pi astics, which mean that out of all the pi's, we are looking for those pi's which are the best pi's for us. What is best pi, which is going to give us the V asterisk and the Q asterisks. And this is actually the whole process, that once we understand, we can somehow now understand how can we solve such an MDP. The solution right now is going to be using the DP. And the thing is that firstly, we need to figure out how to evaluate a policy. So if I give you a policy which is good or bad, we do not know. Probably it's a random policy. And from that random policy, if we start, and can you tell me that how good is that policy, which means that A policy is as good as if you can somehow figure out that under this policy how good is a node, how good a state is, which means that for that pi we need to find out the v's and the q's, and these v's and the q's are actually going to tell you the evaluation of a policy. If you give me a policy statement, I need to find out what is its corresponding v's and the corresponding q's. And then is there a way, once we understand that given a policy this is the goodness or the attribute of a policy, is there a way by which I can iterate or change my policy in such a way so that my policy got updated and become slightly better than the previous one? And how it is being done, because we understand that that these are actually optimal behaviors we are looking for, and if there is any optimal behavior, then anything which is in between or any sub part is also optimal. So iterations are going to be happening, and iterative update is going to ensure that that suppose that if I have got a q0, then I'm using this q0 to somehow come up with q1 which is slightly better than my q0, and then from q0 I will go to q1, then I will go to q2, then I will go to q3, and at some point of time I'm assuming that this becomes better and better and started to some qt, which if t is sufficiently large, then we can say that it actually reached to the optimal solution of our the q, optimal q. So the point is that once you have got this optimal q, that is the solution of your MDP, and it's also being proved that with sufficient large t's, you are this process is going to be terminated. So basically, we are assuming policies or value functions which are at ith step, they are optimal, and using those things, we are trying to estimate our I plus 1th step policy values or the policy functions or the value functions or the q value functions. Yes, a DP revision in the last class I have given, and the point that I wanted to somehow explore or talk about was that suppose that you wanted to go from V to T. The important thing is that if you know the optimal behaviors from here, then you just have to take that thing, because you know that the I minus 1 optimal solution from here is for W4 you know that I minus 1th optimal solution, and for all of them you know that what is the I minus 1th optimal solution. Then you choose the one which is giving you the best from here, and just out of this what is the one which is going to give you the best possible, assuming that this is giving you the best, then you just need to take CVW2 plus this value, and that is the thing anyways is happening as well in our case of state transition. So suppose that you are at this state and you know that from this you are going to get the maximum discounted reward, then you are using this plus this reward. So that was the optimality constraint which is being incorporated in our shortest path solution, which is saying that this mean, and that's why you can see that ith ith optimal solution is being dependent upon I minus 1th optimal solution. Yes, so now we are going to do the first step of policy evaluation. Slowly we will go, and this figure is shown in front of you and it's being numbered, so we'll go from that. So we are going to evaluate a policy. Given that policy, so I am having that policy pi. Given that pi policy, what I wanted to do is that I'm having this state S. What I wanted to compute is that I wanted to compute the value function for this S at k plus 1th step, and I assume that I have its value function at k. So value function at k is actually being given. Value function at k, what does it mean? Value function of k and given. So value function of k for a pi is given. This is our assumption, because once it is given, we are using this to figure out value function for k plus 1th state for all the states. So if I say that v k pi is known it means that vk pi s1, s2, s3, s4 and all of the states is actually known, and I wanted to know that vk plus 1 pi s1, s2, s3 and s4. So right now I am interested to figure out that given such a policy and such a state, can you tell me that vk plus 1 s, right? So let us unroll this figure one by one. So 1 2, this is the third state, now the fourth. So at state s, you can either go here or here. So this is the exact dynamics of your MDP that I am going to enforce and show it to you. In real world it may be slightly different, but the same thing is going to happen for me right now, that at any state s there are only two possible actions, a1 and a2, that you can have. Fine, who is going to tell you that that which action that you need to take at this state? That is going to be governed by your pi. Always remember that from state, if you want to go to your action, pi is, or your policy is going to tell you. From state, if you wanted to go to the next state, what is the next state? That is going to be governed by the transition probabilities. So we will go to that as well. So first we wanted to know that from s, if I wanted to go to state a1, then pi is going to tell you that what is the probability that if you are at a state this, you are going to take action a1. Pi is going to tell, and the amount of reward that you are going to tell. So here pi a1s, and here it is pi a2s, and then you will reach over here. Now, so if you at state s, if you have taken action a, then you are going to get such a reward. Or at s, if you take action a2, you are going to get this reward. Once you have got these rewards at this state, this point, whatever you have done, you are at state s and have taken action a, then you can reach to state s1 or maybe s2, who is going to govern this my state probability, state transition probability, which is saying that at s to s1 taking an action a1, s to s2 taking an action a1, s to s3 taking an action a2, S and S4 taking an action A2. So you all understand that if you from here, if you reach to this, take this action, or you can take this action, depending upon your action. Who is going to tell this action? Pi is going to tell your action. From this action, which state you are going to be, that is going to be governed by your state action dynamics, that is being fixed and being given by your MDP. And once you reach over here, this is my state, and s1, s2, s3 and s4. So from s, you can come over here, you can come over here, you can come over here, and you can come over here. If I wanted to know that what is the probability that at s, you take an action a1, this is the probability, and at an action, taken an action this, you reach to this state, that is this. So from this, what is the probability you can reach over here is this probability multiplied by this probability. This is the thing that you all need to somehow understand. Yeah, so you understand that you have got. So what I have said is that kth state, the kth iterative time, or the kth step value function is known, which means that if you know that, then vk s1 is known, vk s2 is known, vk s3 is known, and vk s4 is known. Now bottom up, that given these four values, can I use them? Because they need to be optimal. We are assuming that these values are optimal, and if we assume, can I find out the value function k plus 1th step value function for this guy? This is my question. And how can we do that? Very simple. Let us see that I want, what is this? This is the expected reward that you can get when you are at here. I mean, what is the expected reward that you can get from here? What is the expected reward that you can get from here is actually this expected reward that you can get from here and from here. These are the four values that you have, using them. The point is that what is the expected reward that you can get from here, and we interested to know that k plus 1 at such value at step. So what you can understand is that you are going to get this reward. Fine. So but you are not getting this reward with a probability 1. You are getting this reward with such a probability. You are getting this reward with this probability. Fine. So you take this reward and then you get this with this probability and this with this probability. That is why you take this and this, you take this reward and multiply by this, you take this reward and multiply by this, add both of them, add this and multiply by this. That is the actual or the expected reward that you are going to get from this left subtree. Similarly, from the right subtree, what you are going to get, that you take this reward and the expected reward that you are going to get from this, what is that? This reward multiplied by this reward multiplied by this, add with this and multiply with this. Yes, so now let us see it, that what does it mean, and I am going to do it for this particular, you know, path A. This path A, what I'm going to do is that you understand that you are going to get this reward coming over here, you are going to get this reward, so this reward multiplied by this you are getting over here, and this is not fully going to be contributing to the V value for this guy. It's going to be contributed with this value, because every time you're not going to choose this path. So with this probability you are choosing this path. Similarly, for the other guy, basically now we are going to do it for B, then we can go do it for C, and we can do it for D. What are that? RSA1 and the corresponding probability this multiplied by VKS2. Similarly, here when you go, then you need to add RSA2. That's why it's RSA2 and RSA2 for C and D. And the corresponding two values got multiplied with the corresponding expected values that you are going to get for S3. So VKS is going to tell you, S3 is going to tell you how good is this state under a policy which is pi, which is right now fixed. Pi is not changing at all. You are iterate for a given fixed pi. We start with some random value function and keep on evaluating it. And once we evaluate, we keep on updating that function, value function. Right. So here k plus 1s is simply defined as a plus b plus c plus d, which is nothing but this probability multiplying, and for all the actions, this probability is weighing it and multiplying it with rs and gamma and this. Right. So gamma is also here. I didn't have write this gamma, that the discounting. Here it is being also added because you all understand that, you know, this is the immediate reward and this is the upcoming reward. So immediate rewards directly added, upcoming rewards need to be discounted. So discounted upcoming future rewards plus the immediate reward, and being scaled for by the probability so as to get the expected value for each and every action. So so if I say that Vk plus 1, then Vk plus 1 for all the states, this is actually one single vector. Vk plus 1, one single vector for S1, for S2, for S3, and so on. Similarly, this Vk, old Vk, that can be, you know, for S1, for S2, for S3, and so on. So these two vectors got multiplying. So this vector got multiplied with a 2D matrix, that's a state transition matrix, and you will get some value that is going to be discounted and added with the reward function, and that is the closed form solution for such a Vk plus 1. So here you can see that your Vk plus 1 is actually being dependent upon Vk. That's your value function at kth iteration. Transition probability, that is anyways being fixed. That's a reward function depending upon your MDP. If you take all of them, you are going to keep on updating your, you know, Vk plus 1. So you are going to get the value function one by one iteratively. You are going to get the, so you know, the value function related to that pi, which is initially, so pi is fixed, v is initialized randomly. You keep on iterating. At some point of time you will get the value function that for that pi. We are going to come up with a simple example. The simple example of policy evaluation, which is which we are going to do is that Very same simple thing that my MDP question is that these are my terminal states. These are my terminal state 1 and terminal state 2. Other than that, I'm having states 1, 2, 3, 4, and so on. All these states are given to me. Reward function is -1, that if you take at any step, if you take any action, I'm going to penalize you with a value of -1 in any direction. If you go only 4 directions which are possible, you cannot move in the diagonal direction. You can move up, down, you can move up, down, left, and right. And for north, south, east, and west, the probability right now is 0.5. What is this? This is my initialized policy. That is my initialized random policy. I don't know anything. I don't know the environment. I just keep on moving randomly in all possible directions. So if I'm here, I don't know where to go. I will go here, here, or in 4 places with the probability of 1 by 4. Reward function is -1. Gamma is actually 1, so it is undiscounted episodic MDP. What we wanted to know is that how long does it take to reach to some terminal state from any grid point. So if I move from any grid point, then how much time does it take for me to reach to any terminal state? The other thing is that we wanted to compute the optimal policy. What is the best possible optimal policy pi, and how we can get that policy as fast as possible. And yes, so one more thing is that all terminal state episode need to be finished, is finished, and looping is with 0 reward. So which this means that if you reach over here or here, then you are just looping over there without any reward. So just to fulfill the thing. Now next point is that now we are going to evaluate this policy. You understand this is my MDP, how you are moving in that MDP. So states you all know. Yes. So states I know. Action, yes, you know the action. For each and every state, if you take an action, in which state you are going to be, that's the state transition probability that you know. Why? Because I'm saying that right now you are moving in all possible directions and 1 by 4, 1 by 4, and so on. Reward, yes, reward function -1 is known if you move in, if you take any such step, and gamma is equal to 1. So your MDP is defined, well defined for such a problem. Once you define such an MDP, I wanted to find out that what is the pi in which we are interested. So let us see this pi. So right now I am saying that I'm interested to start with such a pi, which is saying that in all possible direction move with a 1 by 4 1 by 4 probability. And V0I, what does it mean? V01, V02. So if I just write it as V0, this is say V01, 2, 3, 4, and so on. I wanted to know that at 0th step, what is the value function for 1, 2, 3, and 4? This also means to say that how good ith state is at for a given policy pi at state 0, and my state 0. So now you can see that all these things are right now 0. These are t's, and all these values are actually to say 0, and I do not know anything special about any node. So everything is right now 0. So V0I denotes the number of steps that are required to reach or move from state or any grid I to a terminal state T. Now you see that that is the the meaning of such a value function. Maximizer and DCFers, here it is that how much amount of time or the steps that you need to take if you are here and going from here to there, which means that V09. Right now I don't know anything, that's why I've said 0. So it's not a correct thing, and yes, that is random initialization, and slowly it's keep on iterating. We keep on iterating over this and find out better and better, closer to the actual we keep on moving towards that. So we take a random policy, and V1 is going to be using V0, and VI is going to be using VI plus 1, so as to get a better estimate of V for that given policy pi. And at some point of time, It's slowly going to converge over there. Now let us compute it once. So this is V0, and V0 is shown to you and everything is 0. Now we are going to find out for V1, and what we are going to do is that this whole matrix is being computed. I'm just going to compute this one value for you, that is V16. We are interested to understand V16. V16, we can take only 4 possible actions with the equal probability 1/4. We can and the actions are north, south, east, and west, and then you are ending up with 2 second state, 10th state, 7th state, and 5th state. Second state, 5th state, 7th state, and 10th state, and the corresponding values are, but not the current values, but the, if you are interested in V1, then you are looking for, you can use V0 values. So we are going to use this. We are going to use this matrix to compute this matrix. And that is the optimality enforcement. We are enforcing that this is optimal right now. Using this, you compute V1 and keep on doing. Yes. So now you can see that V16 is going to be, yes, it is going to be, it's going to be what? It's going to be this reward. And what is that reward? That is -1. So -1. So right now I'm doing it for this. That is -1 plus V02, right? And multiplied by 1/4. 1/4. Then for this is going to be -1 plus V010 -1 plus V010 1/4. Similarly for all of them. You add all of them, and then you will see that these values are anyway zeros. So if they are 0, this is actually -1 plus 0, 1/4 multiplied by 4, and you keep, just compute, you are going to get -1. That is why this -1 is actually coming over here. And all of these values are being computed like this, using this simple formula and this simple optimality constraint. So once you have got this V1, now I will use this V1 to compute V2. Pi is fixed. Now I'm computing V2, then V3, then V4, and it's our assumption that V infinity is actually equal to the value function in which we are interested. Value function for this pi. How we are going to get this V2? Again, all these values are written for you. All these values are written for you. I'm just going to show it again and going to compute it for these two values. These two values I'm going to do. That is right now V26. What V26 is going to be, that you can go here, you can go here, you can go here, and you can go here. So that is V2. So that is V12, V110, V17, and V15. Only 4 values that you are going to use. All of them are right now, values right now, they are -1. All of them are actually -1. So that's why you can see that -1, -1, -1, and -1. And this is the immediate reward. So immediate rewards are always -1 if you take one step. So now you can see that that is equal to -1 plus V12. That is for, that is for this. Then -1 V110. That is for this. Then -1 V17 and -1 V15. You add all of them multiplied by 1/4, and that is going to give you -2. Similarly, if you wanted to do it for this, the important thing over here is that you can move here, you can move here, you can move here. Then that is going to give you what? That's going to give you V1t, and V1t is nothing but actually going to be equal to 0. That's the thing. So here you can move here, and this direction, and in this direction. So but in this direction you cannot go, and it's been defined in your MDP that in this action, if you take any action which is out of the bound, then you are keep on looping in that, keep on looping in the same state. So so here you can see that this is for V113, this is for V110, this is for V1t, and this is for V1 down at 14, which is again V114. So V114. So you can copy these values from the previous matrix. They are -1, -1. This is anyway 0, and this is again -1. So this is going to give you 1.75, which is being rounded off over here. So now you see that from V1 you have got your V2, And once you have got your V2, similarly, you can get your V3. Very same things here. I have computed it for V3 2. So you all understand that I'm going in this direction, in this and in this direction. In top, I am going in only V2 2 we are going to get. So that's why you can see that V2 2, then V2 1, V2 3, and V2 6. And the value is actually minus 2.92 or so. So in this way, we can evaluate a policy. Given any policy, we keep on iterating over the value function. Randomly initialized value function. We keep on iterating so as to get the V pi. Clear? So for a policy function, we understand that how we can evaluate that policy function. Now we are going that once you know how can you evaluate a policy function, how can I improve such a policy function? Because for V1, V2, V3, whatever you have got, all of this thing is actually talking about a pi, which is a randomly initialized policy. But we are interested to know that what is the good or the best policy. How can you iterate over your policy so as to update it in such a way so that you every time keep on getting the better and better policy, and your distance between your policy and the optimal policy is somehow reducing, right? So the policy improvement with the exact same problem, I'm going to show you the policy improvement as well. These are the actions which are possible. This is the reward that you are looking for. You can get. These are the two states over which you are going to be terminating, and all remains to be the same. Now see that for any given MDP, we know that how we can evaluate a policy, right? And say for some random policy, once you have got a value function, given that value function may be some vk, when you assume that it got somehow saturated, given that vk, you can take one action. And how can you take an action? You just have to take the action in a manner, greedy manner. What does it mean? You are at any state, you just see what are the value functions. If I go this direction, this direction, this direction, and this direction, and choose to move in the direction which is giving you the minimum minimum such reward, because reward here is actually a punishment. Let us see it again. So we just going to choose the greedy action with respect to the value function, and you can see that from value function you will get a policy. So first of all, let us see that suppose that this is my policy. With respect to this policy, I will get this, and I initialize it. So this is my random policy, and this is my value function, which is all 0. Given this value function, I can get such a value function. Now given such a value function, I may come up with a policy. What is that? This is just, you see that at this point where you wanted to go. I do not want it to take all possible directions with equal probability. No, because I know that if I move in this direction, I'm going to get a 0. At this point, you see that you do still at this point you do not get a effective answer. At this point still you feel that I don't know, and in each direction it is -1, so I will take 1/4, 1/4, 1/4, and so on. But at this you have got some answer. So at this you see that this is my initial policy, and this policy says that in this direction I am going, in this direction I am going, in this direction I am going. So the states which are near to the terminal states, after first iteration, I started to somehow get better decisions, and the policy is actually changing. So that was pi random, and this can be my pi 1 first policy. So that you can see that from this and this I got this, and from this value function I have got another policy. This is my pi 1 policy. Now right now I am not saying that you just change your policy from pi to pi 1. I am just saying that if you have a value function, if you have such a value function, from this value function you can get another value function, and with this value function you can get another policy as well. So don't, for every step, you don't update your policy. Let your value function somehow converge. Once your value function got converged over that value function, you update your policy. So it may be the case that I have a policy, I take a value function, I keep on getting it converged. When this function got converged, I update my policy. And from this, you have got from pi random, you have got another policy, pi 3 or some other pi dash policy, and keep on iterating over this policy again. So you fix a policy, randomly select some value function, iterate over that value function, get that value function converged. Once your value function got converged, act randomly and come up with a new policy and keep on doing this business again and again, so that your value function keep on so that your policy keep on converging towards the actual optimal policy, right? Yes. So now you can see that what in this figure what we're trying to show is that for k equal to 0 and 1 and 2 and 3 and 10 and then infinitely. So at infinite you can see that between k10 and k infinity still some variation is happening. But the good thing is that here it is random policy with respect to this function, with respect to this value function. This is the policy with respect to this value function. This can be the policy. So you see that policy 1, policy 2, policy 3, and after that k3 and k5, very soon you will see that these values keep on changing, but your value function is almost fixed. And in simple MDPs very easily or in some few steps your optimal policy function can be achieved, but usually it is not. So you can see that these values are changing, but once you assume that okay, after k equal to 5 or k equal to 10, whatever the value function I am getting, I will take its policy and I update my policy from pi random to that policy, and then that is my pi 1 or pi dash. Then that's going to be my pi dash, and over that I keep on iterating again over the I wanted to find out the value function for that pi dash, and keep on doing till you get better and better policies. And at some point of time when you stop to get better policies, which means that you actually have got the optimal policy. So that is what, that from v pi you have got another reference pi dash. That's actually the greedy version, greedily if you act over that v pi. So given any policy, evaluate that policy, iterate value function over that, and improve your policy from pi to pi dash. That is your policy evaluation and policy improvement, and keep on doing in a loop. So you can see that starting with a value function and a policy, first you evaluate that policy and then greedily act over that, and then again evaluate over that, and then greedily act, find out another policy, then evaluate, then again you greedily you find out another policy and keep on doing, and at some point of time you are going to get the optimal value as well as optimal policy. So that is actually the policy iteration which is going to happen, and it's being actually properly being proved that in such a scenario in which you just first choose pi, then v, then greedily, and then keep on doing moving in this such a loop like this, then no matter from where you are starting or initializing your pi and v's, it's bound to converge. Only thing is that initialization are just going to affect the rate of such a convergence, right? So with this whole understanding, we can somehow give you the glimpse of deep q learning, because so you understand that MDP is being defined. Over that you need to choose some pi astic, which means that you need to know q astic or v astic. We are interested to somehow know, once I know that what is my q astic, that is the solution, because from this q astic I can act greedily so as to get the optimal such a policy. So you have got a policy. So is there someone who can tell me the deep Q learning is, so how can I get this Q? So Q astic can just have shown you the iterative solution to get this Q. Now let us see that why such a solution fails, and what is and why we move towards deep Q learning. So now you can see that the way in which V astic was defined for every S, Q astic is also defined for all S comma A. At any state S, if you take an action A, that what is the max, the expected reward that you are going to get, and that is being defined like this. This is the immediate, this is the discounted, and this is being maximized for that S dash, and for all the S dashes, and for all the actions over that S dash, you maximize. And this is the thing we just have seen. It is just coming from the above thing where we have defined V astic S. Q astic will so Qi, whatever the Qi that you have, if you take your key, up to infinity, it is definitely going to be converged into Q astic. This is first thing. And at each step, we have to enforce the Bellman optimality. We are enforcing that Bellman optimality. This is the way where we are enforcing the Bellman optimality, and the equations are being defined recursively. There are few problems with such a DP solution, because if you have a DP solution, then exactly you can compute this Q astic and as well as pi astic. But the point is that we need to evaluate and improve. Fine, we can evaluate and improve, and we have already given you the equations for this. And it's also being proved that it's going to convert, so there should not be any problem. But the problem here is that state S. So this state S, suppose that you are trying to learn how to play, let your Atari, let your agent to play this Atari games. You need to somehow manage that what are the given states which are being there, and states are simply raw image pixels. And how many such image pixels or states can be? This S can actually be exponentially many, and for each and every S, I assume that your A's or your actions are fixed. Some limited amount of actions that you can take, but S comma A is going to be a very huge or infinitely big search, state action space. And for each and every state action space, you need to find out the Q, S, comma, A, maybe T, and T is going from 0 to say some infinity, or maybe some fixed number, and it's simply out of scalability. So you cannot simply compute such a thing, because it's going to be computationally infeasible. So instead, what one should have to do, so instead of, in such a game, in such a scenario, when your QS comma A is simply not computable, we need to come up with an approximator, which is going to tell you, and I will tell you that how this approximator is going to work, because even for the case of approximate can approximate the thing, but S comma A is still huge and exponentially large S comma A space. How can you come up with an a function which can solve something which is exponentially populated? But still, first of all, let's understand that what is the feeling behind, or the intuition behind this deep Q learning, that that we wanted to learn this. So instead of learning it via DP, we say that we wanted to learn this function which is being parameterized over theta. So QS comma A is a function parameterized over theta. We wanted to learn this theta using some DNN function, so that whenever I have this theta, I give this SA to it, it's going to give me a value that has to be as close as possible to the Q astic S comma A. That is deep Q learning, the objective of your deep Q learning. But the catch is that this is not even known. There is no label. It's not a supervised thing in which you just take this thing and subtract it, and that's your nice and clean loss function and you are done. No. Now let us see that what deep Q learning actually does. So we are saying that this is our neural network. At any point of time, say theta I are the parameters, And right now you can say that theta t are the parameters at some time state. I take s comma a, show it to my network. This network is giving me qs comma a theta I, or maybe qs comma a theta t, and that is what the tth version of my q. You all understand that t is actually varying from 1 2 3 4, and at some point of time t is going to become so high. At some point of time your q actually started to converge towards your qst. That's being proved somewhere. So I am trying to say is that at any time t, whatever the parameters that you have, show your st, you are going to get some value. That is your estimate of qt. But these are the optimal behaviors, and Bellman inequality, Bellman equality, or the Bellman condition should have to be enforced. How you are going to enforce the Bellman equation is that this s comma a, I have got two neural networks. If I say one neural network is this theta t minus 1, one neural network is this theta t. So I will use this neural network, show it s comma t, and use this equation, right? So what I am trying to say is that I have neural network this, I have neural network this neural network I am showing s comma a and using it over here. That is the label for me, because it need to say that your first neural net, you know, the neural network parameters at t minus 1, they are going to give me the estimate of same q but at t minus 1 state. I'm using that, getting yi. That should have to be the label for such a thing. Now what is going to be the loss function? Yi minus this thing. I is the Bellman thing which is actually coming from the Bellman optimality. It has to be like this, but it is actually this. How can I improve my my theta parameters so as the Bellman optimality is enforced? This value should not be any arbit thing. It has to be as close as this. So your network keep on iterating over this. So this is just the beginning, or the initial forward pass. I will talk about it again in our next lecture.